So now in this lecture we will discuss about memory addressing. Already we discussed that RAM and ROM, these two type of memory which are basically a semiconductor memory, we can connect with microprocessor. Now memory addressing. In case of memory addressing, first of all we should find that how much maximum memory can be connected with a microprocessor. To find out this, we have to know how many address lines are there in microprocessor. So we will take one example. Let us assume we have one microprocessor with 16 address lines. So if a microprocessor is there with 16 address lines, then how much maximum memory we can connect? So for that, simply apply the formula 2 raised to the power number of address lines. So here number of address lines are 16. So in this way we can calculate the total number of maximum locations, right? So already we know that if there are 10 address lines. So here I will write address lines, and here a maximum memory which we can connect. So if there are 10 address lines, then already in previous lecture we just discussed that with the 10 address lines we can connect 1 KB memory. So if there are 11 address lines, then just double it. It will be 2 KB. If there are 12 address lines, then we can connect maximum 4 KB memory. If 13 address lines are there, then we can connect maximum of 8 KB memory. If 14 address lines, then we can connect 16 KB memory. If there are 15 address lines, then we can connect 32 KB memory. And if there are 16 address lines, then we can connect 64 KB memory. So now with a microprocessor having 16 address lines, we can connect maximum 64 KB memory. And this is maximum, right? Now this 64 KB memory will be maximum memory. So suppose we are having a RAM of 32 KB. So this 32 KB RAM we have connected with this microprocessor, and we want to connect one ROM also. Then what can be the size of this ROM? So 64 is the maximum. 32 KB already we have utilized for RAM. So remaining 32 KB maximum we can use for ROM, right? So here when we talk about the maximum capacity, then here we can connect a memory with lower capacity. That is possible. But we cannot connect a memory with higher than 64 KB in this particular case. So here, suppose another case I will take. I want to connect a RAM of 16 KB and ROM also 16 KB. Right? Only this much memory I require, because it depends upon the application. In which particular application we are using this particular microprocessor. We know that in our application we require only this much ROM. Then what is the need to connect 32 KB? So why unnecessarily we shall pay extra money for the memory? So here, suppose in our application we require only 16 KB ROM and 16 KB RAM. So in total, now it will be 32 KB. So total we are correcting now 30 kb, and out of 64 kb we are only correcting 32 kb. So this is possible. So depending upon our application, we shall first find out how much memory we want to connect. So now suppose in our application we want to connect one RAM of 16 kb and one ROM of 16 kb. So RAM 16 kb and ROM 16 kb. Okay. Now with this memory, we have to now find out what shall be the addresses of various locations of this 16 kb ROM and this 16 kb RAM. Unless we know the addresses, we cannot access the content of the address. So now how to define the addresses, right? So suppose now first we will define the addresses of RAM 16 kb ROM. First we will take ROM addresses. Now here in the microprocessor and microcontroller programming, we will use hexadecimal number systems. Now since this is a processor with which we want to connect this memory, so this is our microprocessor and it is having 16 address lines. So address lines are from A0 to A15. These are the 16 address lines, right? A15 to A0. These are 16 address lines. Now these address lines will be connected with the ROM. So first of all, what we will do, we will write these addresses lines here. A15, A14, A13, A12, A11, A10, A9, A8, A7, A6, A5, A4, A3, A2, A1 and A0. These are all the address lines which are coming out from the microprocessor. Now we have 16 kb ROM. So with the 16 kb ROM, we have to decide what shall be our starting address of this ROM, right? So in this ROM, suppose now this is a ROM. This is a ROM of 16 kb. In 16 kb ROM, this is location number 0, this is location number 1, like this. When we will go at the highest location, then here the last location will be 65,535. Basically 16K means 65, no, this is not 65,000, that is for 64K. So we'll find out what will be the last location. So location number 0, 1, 2, 3, like this, there will be some last location. Now as a designer, we have to first decide what shall be the address of my first location. So let us assume the address of my first location is 0000H. So here this H indicates hexadecimal number system. In hexadecimal number system, this 0 of hexadecimal, if we write in terms of binary, then it will be 0000. These are 40 binary. Again, this 0 is a hexadecimal 0. Write it in binary 1, 2, 3, 4, 4 zeros, like this. This is third 0 in binary. These are 4 zeros. This 1 0 of the hexadecimal equivalent to 4 zeros of binary. So basically, this is the address of my first location. So how many binary digits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So here we are having 16 address lines. So we will write this address here 0, 0, 0, 0, this 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So this is my starting address. So starting address in terms of hexadecimal 0000H. This is hex number, hex address. Now here we are having 16 KB ROM. So first we shall find out in this ROM how many address lines will be there. How many address lines will be there? So again, with 10 address lines, we can connect 1 KB, with 11, 2 KB, with 12, 4 KB, with 13, 8 KB, with 14, 16 KB. So for 16 KB memory, we require 14 address lines. So in this ROM, if we purchase 16 KB ROM from the market, then we will find that in that 16 KB ROM, there will be 14 address lines. So we will write those address lines A0 to A30. These are 14 address lines, A0 to A30. Right? Okay. I will draw this here. This is 16 KB ROM. So here we are having address lines from A0 to A30. Total 14 address lines are required for 16 KB memory. Now what we will do? These are the addresses coming out from the microprocessor. So what we will do? A0 to A30. You just put one mark there. A0 to A30. We will put one mark here. Right? So only these lines A0 to A30 from the microprocessor will be connected to your ROM. So in our ROM, we will connect A0 to A30. These will be connected to our address lines of our ROM. Now, the leftover addresses lines are A14 and A15. A14 and A15. These two lines. Now, these two lines are used for selecting this ROM. That is for chip selection. So these lines will be used for chip select. Right? So already in last lecture we discussed that in this ROM there is a pin which is called as chip select. Right? That is active low pin. So to select this particular memory, this pin must get 0. So now here we have to design one decoder circuit. We have to design one decoder circuit so that this memory should be selected. For that, what we will do? You just connect here one NAND gate. You connect here one NAND gate. The output of the NAND gate is connected to CS bar. Now these two pins which are coming out from the processor A14 and A15 will be connected to this NAND gate, right? And just you remember one thing. If just concentrate here for A14 pin, this A14 pin, the value of this A14 pin is 0, right? So if it is 0, then connect this A14 pin via one inverter. So what we will do? We will connect this through one inverter. This. Now you come to next address line A15. Now this A15 address line, what is the value here? It is 0. If it is 0, we have to connect this A15 line to this NAND gate through one inverter. Through one inverter. Like this, you connect. Right? Now, as usual, this is a ROM. So, in case of ROM, since we can only read from ROM, that's why there is one pin called as read bar, right? Since we cannot write inside this ROM, that's why there is no write pin in ROM. Whereas in last lecture we discussed about RAM. In RAM we just found that there is a chip select, there is a read bar, and there is a write pin also, right? But since ROM we cannot write, that's why we don't have that pin. Now this read bar will be connected to read bar signal of our microprocessor. It will be connected to read bar of microprocessor, right? So now the starting, what will be the starting address of this memory? 16 KB ROM, 16 KB ROM. So starting address is 0000H. In hexadecimal we will write. So location, this location number 0, and it will have an address 0000H, right? What can be the next location? Next location address, next location is location number 1. So next address will be, keep this same. These value will not change. It will remain 00. And now this will change. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Right? This in a decimal number system, in binary number system, after this first value, the next value will be this only. Right? So now in this case, now in hexadecimal, if we write this, then this will be, these 4 group of the 0 will be 0, 1, 2, 3, 4. This will be 0, 1, 2, 3, 4. This will be 0 and 1, 2, 3, 4. This is 1. So 0001H. This is the next address, 0001H. This will be the next location address. Now, in this way, if we move, we have to make A14 and A15 constant. These values should not change. So, only A0 to A13 are allowed to be changed. So, how much maximum value you will get at A0 to A13? So, maximum will be, all these can be 1. So, this is the maximum. So, in this case, again A14 and A15 are 0. So, what is this address now? 0011. 0011 in hexadecimal it is 8421, means 3. This is 3. After this, 1111. This is F. 1111. This is F and 1111. This is F. So last location address will be 3FFFH. So if we design this decoder in this way, A14 and A15 are connected to this NAND gate through the inverter, and A0 to A13 pin, address pin of the microprocessor, are connected to A0 to A13 pin of memory, then in that case the memory map means the memory range. The memory range, address range of this 16 KB memory will be from 0000H to 3FFFH. This will be the memory range. Any address you send apart from this will not activate this particular memory. For example, if I will send 0300H and this address, I will send this address over these address lines. Now what will happen? You just say 0300. 0300 means this 0. 0003. 0011. Then 0. 0000 and 0000. So basically over the address lines A0 to A15, this particular binary pattern is flowing. So now what will happen? A15 and A14 both are 0, 0. So here you will have 0, here you will have 0. There is an inverter. So what inverter will do? It will convert these two 0 in 1. Right? So both the inputs of the NAND gate are 1 and 1. So now what will happen? What is the output of this NAND gate? If both the inputs are 1, so here you will get 0. So if here you will get 0, then this CS bar will get 0. And once it will get 0, this chip will be selected. It will be activated. Now once this chip will be selected, then depending upon the value of A0 to A30, this A0 to A30, any one particular memory location will be activated. And once that memory location is activated, now depending upon the signal over read bar, that data is available over the data line, and from the data line it will enter inside the processor. So this is one example of interfacing of ROM. Sorry, this is ROM. Now in our example, we want to interface 16 KB ROM with the starting address 0000H. Right? So in this case, we concluded that the last address will be 3FFFH. Now we want to connect one 16 KB RAM also. Right? So no two memories can have same address. Right? So here address must be different. So let us assume that for this RAM, I want the starting address as 8000H. Right? That should be my starting address of this 16 KB RAM. So we will find what will be my last address. Right? What will be my last address? So for this, again, first you find out for the 16 KB RAM, how many address lines are required. Just now, in the case of ROM, we have calculated that for the ROM, 16 KB ROM, we require A0 to A30, total 14 address lines. So same way in this case also we require total 14 address lines. Right? That is from A0 to A30. So this, we will put one mark here, A0 to A30. Now, the starting address is 8000H. So we will actually hexadecimal. Write this hexadecimal numbers in binary. So 8 means 1000 is 8. Then this 0. 0000. Then next 0. 0000. Then next 0. 0000. This is the address 8000H in binary form. This is the address. Now, what we know that we cannot change the A14 and A15. These must be same. They must be constant. So, we will make these constant. And what will be the maximum value which we can flow over A0 to A13? It can be 1111, 1111, 111111. Right? So now this will be my last address. So last address, write in hexadecimal 1011. So what is the meaning of 1011? 8421. So this is 8, 9, 10, 11. 11 in hexadecimal is B. These 4 ones are F. These 4 ones are F. And these 4 ones are F. So the last address is now B, F, 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 H. This will be my last address of this 16 KB RAM if the starting address is 8000H. Now simply draw the interfacing circuit. So how we will draw the interfacing circuit? I will write this last. A14 and A15. A15 is 1 and A14 is 0. Right. So now connect here 16 KB RAM. 16 KB RAM, we have address lines from A0 to A13. So these A0 to A13 line address lines will be connected to A0 to A13 address lines of microprocessor. So I will connect these A0 and A13, right? Now A14 and A15. These lines has to be connected to this NAND gate, and the output of the NAND gate has to be connected to CS bar. And how we will connect? Just A14. A14 will remain 0. If it will remain 0, connect it through NOT gate. Right? And A15 is 1. If A15 is 1, connect it directly. That's all. Connect here. And there is a write bar and there is read bar. Right? So if in this way we connect, so this is our decoder circuit. If we connect the decoder circuit in this way and A0 to A13 we have to be connected here, then the memory map, the addresses of this will become 8000H to BFFFH. These will be the addresses of all the locations of these 16 KB RAM. Okay.